Let's solve the following problem. Compute the polar or exponential form of the following number, and we have the complex number z that is equal to 1 minus root 3 times I. Okay, so what we are asked to do is to compute either the polar or the exponential form of this complex number, which is given in its algebraic form, as we call it. So we have the real and imaginary parts given to us, and what we have to now do, in effect, is to calculate the length, the modulus of this number, and the angle, the argument of this number. For this, it might be useful if we sketch, if we try to locate this number in the complex plane. It will give us a good check whether our results that we'll get make sense or not. So here is the complex plane with the real and imaginary axes in which we can locate various points. So if there is 0 in the origin, we have to choose a unit of distance. Let's say here is 1, here is the number 2, and so on. And the same thing can be done in the along the imaginary axis. So if you just sketched this out like I do, so you could locate roughly where this point might be in the plane. Well, it has a real part 1, so we have to walk along the real line in the positive direction to 1, and then we have the imaginary part that is negative square root of 3. The square root of 3 is roughly 1.73, so we have to take the negative of that number, so it means we have to walk down to roughly where the negative root 3 might be on the imaginary axis. So let's say here is negative root 3, and the intersection of these two lines will have our number represented by this dot. So what we need is to calculate the length of the segment of the line segment that connects this point with the origin, and we also have to calculate this angle right here. So the first thing is the length, and the second one is the angle. So let's see. Well, the length r is the modulus of our complex number, and it can be calculated by taking the squared sum of the real and imaginary parts and then taking the square root of that number. So we'll just simply take the squared sum of the real and imaginary parts to get 1 squared plus negative root 3 squared under the square root. So this is 1 plus 3, giving us 4 under the square root, and the positive square root of 4 is plus 2. So we have the length of this number. This is plus 2 units. Well, my drawing is not perfect, but basically this should be 2 units of distance away from the origin, this point. For the argument for theta, we usually, well, let me just change this real quick, because we usually used the Greek letter phi for this. So let me just stick to what we've been using in the lectures. So phi, the argument of our complex number is now have to be calculated using what we learned. It's the arcus tangent function, the inverse function of the tangent function applied to the ratio of the imaginary and real parts of our number. So it's minus root 3 divided by 1. So if you put this into your calculator, you should get, or if you remember sort of the special values for the trigonometric functions, you should get and remember that you get this value for negative 60 degrees, negative pi over 3 radians. So in fact, that is what you should get, so that's minus pi over 3 radians. Okay, negative 60 degrees is this angle. Okay, so now we are ready to write our complex number in its polar form, which is just the modulus multiplied by the cosine of the argument plus I times the sine of the argument. So in this case, z is simply twice the cosine of negative pi over 3 plus the sine plus I times the sine of negative pi over 3. And if you want to write this in the exponential form, you have to take these two numbers again, the modulus and the argument, and you just take twice e to the I times the argument. So modulus times e to the I times the argument, so it's minus I times pi over 3. Okay, this is the solution to our problem.